My name is Megumi Sano, and today I will be presenting on learning in social environments with curious neural agents. When you look around in your environment, you might notice that the world we live in consists of stimuli with a diverse range of dynamics. For example, some objects, like these blocks, are static. Some stimuli, like the ceiling fan, are a little more dynamic, but still predictable. On the other extreme, some, like the rustling of the leaves in the wind, are very random and difficult to predict. Somewhere in all of these dynamics are a very important class of stimuli, animate. They behave with considerable unpredictability, but also considerable regularity. They have goals and other internal states that allows us to predict their behavior to some reasonable extent. As you can see, the world we live in consists of stimuli with a diverse range of dynamics on the learnability spectrum, with static and periodic dynamics being easier to learn, noise-like dynamics being almost impossible to learn, and animate dynamics lying in a sweet spot between them. Now imagine you're an infant in this world of blooming, buzzing confusion. What will you look at? How will you go on learning about the world when there's just so much to learn? How will you allocate your limited time and attention to learn about the various stimuli around you? Now, before we formalize this problem, what do we mean by learning about the world? One possible answer is that humans have the ability to learn world models, self-supervised predictive models of how the world evolves. One example of this is a forward dynamics prediction model, which takes in past observations and the actions that the agent took as input and outputs predictions of what will happen next. Learning world models gives us compact abstractions of high bandwidth sensory inputs, the ability to plan across long temporal horizons, and an understanding of the behavioral patterns of other agents and objects. The key idea here is that the data that these world models are supervised on are collected by the agent itself. So, while you have the world model problem asking what happens next if I take action A, you must also solve the policy problem, which asks what should I do in order to gather good data for my world model. In other words, the overall problem becomes how can an agent actively explore its environment in a way that maximizes world model learning? We call this problem the active world model learning problem. More formally, we frame it as a reinforcement learning problem, finding a policy pi such that the expected reward over the data gathered from that policy is maximized. If we want to maximize world model predictive performance, then it makes sense for the true objective to be the negative of the world model loss. However, this true objective is not known in advance and expensive to evaluate, which motivates the need for a proxy reward that promotes the same learning goal as the true objective while being computationally efficient. Since such proxy rewards do not relate to a specific external task, past works have called such proxy rewards intrinsic rewards, or sometimes more specifically, curiosity. So now that we have formalized the problem, our goal is to build a curious neural agent that can efficiently learn world models in real-world-like virtual environments containing a diverse range of dynamics on the learnability spectrum. For the rest of this talk, I will first describe our virtual environment design and then talk about our curious neural agent implementation. So how do we design a virtual environment that is a distillation of the real world containing these diverse stimuli? To do this, we reduce the stimuli to hard-coded spherical robots, which removes any visual confounds while preserving the core dynamics of the stimuli. We call these stimuli external agents to distinguish them from our curious neural agent. Here's what our virtual environment looks like with the curious neural agent, the white robot in the middle. The curious neural agent can rotate around to look at the different external agent behaviors around it, as you can see in the first-person view. In each quadrant of the room, we have a couple of stationary objects, as well as one external agent behavior, which consists of either one or two external agents. Each external agent behavior is either inanimate or animate. The inanimate behaviors are either static, periodic agents, which move back and forth between 2 points, and noise external agents, which move in randomly sampled directions in its quadrant. The animate behaviors include reaching, where the agent approaches each object in its quadrant such that the object positions fully determine its trajectory. In chasing, the yellow agent chases the white agent. In peekaboo, the peekaboo agent acts contingently on the curious agent. If the curious agent looks at it, it hides behind an object. If the curious agent keeps staring at it, then it starts peeking from behind the object. And if the curious agent stops looking at it, it comes back to its original exposed location. And finally, in mimicry, the white agent imitates the yellow agent. We also designed stochastic variants of each of these animate behaviors, such as adding noise to the imitator agent in mimicry to make the imitation imperfect. So, given such an environment, how do we design a curious neural agent that can efficiently learn world models in it? Recall that what we ultimately want to do is to minimize the expected loss of the world model. So one idea would be to use the world model loss as the reward. However, this leads to the agent attending to noise-like dynamics in the environment, since world model loss stays high on these stimuli. This is often called the white noise problem in artificial curiosity works and leads to suboptimal world model learning. We propose gamma progress curiosity, a computationally efficient method of calculating world model learning progress and using that as the curiosity signal to motivate the curious agent to look at stimuli that it can make progress on, so stimuli that are complex yet learnable. In particular, we use theta old and theta new, where theta old is a geometric mixture of past models and theta new is our current world model, and use the difference in their losses as the curiosity signal. We term our method gamma progress, where gamma is the mixing parameter used in the update rule for theta old. So at a high level, our curious neural agent takes in observations from the environment, which are encoded into object-centric representations, essentially capturing the coordinates of the agents and the objects, which are fed into the two world models parameterized by theta new and theta old, and we take the difference in their losses as the reward to update the policy. We evaluate our curious neural agent in two settings. The first one is the mixture world, which is a distillation of the four representative dynamics present in the real world. The second one is the noise world, which has one animate behavior and the rest are noise behaviors. This is to test whether the curiosity mechanism is robust to the white noise problem. We measure world model performance on validation prediction tasks as a function of environment interactions to evaluate the efficiency of world model learning. We compare our method, gamma progress, to prior works in artificial curiosity. The first one is adversarial, which uses world model loss as the reward and is often susceptible to the white noise problem. Random network distillation is a novelty-based method that trains a predictor neural net to match the outputs of a random state encoder. Delta progress, also known as surprisal, stores an explicit old model k steps behind. However, this requires storing k past models and can be computationally intractable with high values of k. And finally, with model disagreement, we use the variance of the predictions of an ensemble of n world models as the reward. In addition to these curiosity signals, we also compare our method to random policy. So how does our method do on predictive performance? Here, I am showing you visualizations of the ground truth trajectories of deterministic chasing, and the translucent spheres are the world model predictions made by world models trained by the different curiosity signals. And you can see that our gamma progress method clearly outperforms other methods. We can quantify this by looking at the end predictive performance of the world models in both the mixture world and the noise world across different behaviors. gamma progress in dark blue attains highest end predictive performance. This shows that our progress curiosity signal is consistent with the true learning objective. So our method learns good world models. However, our method not only learns good world models, but also learns them faster. So here I am showing the loss of the world model, the validation loss of the world model across environment steps, across training environment steps. And so the lower the loss, the better the world model predictive performance. And we can see that gamma progress attains lower loss earlier on in training than the baselines, showing that our method is able to learn world models with less environment samples. We were also interested to see whether our curious neural agent shows animate attention. Various cognitive science works suggest that humans preferentially attend to animate stimuli over inanimate stimuli from a young age, and that this kind of attentional behavior is prevalent even in the absence of visual features such as faces. Dynamics that are indicative of animacy are sufficient for animate attention to arise. And because our curious neural agent is trained to look at stimuli that it can make progress on, it makes sense to expect that it would attend most to animate stimuli, which lie in the sweet spot. And indeed, that is what we found. Here I am showing you total animate attention, which is the ratio between the time spent looking at animate behaviors versus the noise behaviors, and gamma progress attains highest total animate attention. We can also zoom into one of the behaviors, say deterministic chasing, and look at the animate and inanimate attention differential across environment steps. Gamma progress curiosity attains high animate attention consistently over time, whereas crucially, other methods such as disagreement and adversarial attend more to the noise behaviors than random policy, indicating the effect of the white noise problem. So unlike the standard hypothesis that the brain has a built-in animacy detection module, we show that with the right type of curiosity signal, animate attention, a prevalent human behavior in social environments, can instead arise from a more general curiosity-driven learning process. We're also working to compare this attentional behavior of our curious neural agent to human subjects by creating similar displays in the real world and measuring the attention of human subjects using a head-mounted eye tracker. And our preliminary results show similar attentional patterns between human subjects and our curious neural agent. Another exciting future direction is modeling the developmental variability of human attention. Autism spectrum disorder is a developmental disorder characterized by both low-level visual attention and high-level social acuity. While attention is often easy to measure, social acuity is difficult to measure, resulting in subjective, expensive, and often too late diagnosis. We set out to seek whether it would be possible to predict later social acuity differences based on earlier attentional behavior. In the case of our curious neural agent, we define social acuity in terms of social prediction performance, the ability to predict other agents' behaviors, which is basically our world model performance. Our regression results on the curious neural agent data suggest that indeed early attentional behavior is a good indicator of predicting later social prediction performance, and perhaps somewhat more surprisingly, a better indicator than early social prediction performance itself. So, while this is obviously a hypothetical model and this direction needs a lot more work, we are excited about this potential link between early attentional behavior and later downstream social acuity differences, as it could be a good first step towards more objective diagnostics for autism spectrum disorder. Thank you for listening.